Hello everyone. In this video, we are going to talk about the impact between rigid bodies. If you remember, in one of the videos under the dynamics playlist, I have talked about impacts between particles, right? And that's where you do not care about the rotation of that part, and all you care about are the velocities before and after impact. Now, when two rigid bodies hit each other, not only you have to find and care about the velocities at their centroid, you also need to find the omegas, the angular velocities after impact, if you know everything before impact. Like this example here, these two cars are coming at the same point. Okay, let's say they don't see each other, or maybe they do, right? They want to have an accident. So each car is about 1600 kilogram. Their moments of inertia about the centroid are 960 kilogram meter squared. They come, and then at this point, they hit each other at point P, where the common tangent between the two surfaces is along x direction, and the common normal along which the impact force is exchanged is along the y direction. The speeds of the centroid are given before impact, 20 and 30. The direction of motion are given. The distance between the centroid to the contact point P for each one is given. They are two identical cars, so you have the dimensions here, and they do matter, this 1 meter and 1.8 meter. And they are not doing any steering, they are going straight. So the omegas before impact are 0. If you use a coefficient of restitution of 0.2, and we assume that where they hit each other there is no friction, so all the force exchange is along y direction. Okay, this is just to simplify the problem. In real world, really there is friction between the two surfaces when they are touching each other. There is always friction, so here is just to simplify the problem. But even if that is the case, then you need to find the omegas of each car after impact and the velocity of the centroids after impact. So you might say, what happens if friction comes in? Well, if friction comes in, then you cannot use the conservation of the total linear momentum. And what you need is you need to know the impulse of the friction, okay, because the friction is going to be mu k times n, and n here is the force of impact, which we don't know clearly as a function of time. So if we want to calculate the change of total momentum in the x direction, then what you will need to have is the integral of that impact force versus time, which is called the impulse, linear impulse, and multiplied by mu to basically get the amount of change. And so here in this problem, to make the problem a little bit simpler, it is neglected, so it is like the mu is very small. So now, what principles can be used to solve for the unknowns? Well, we have the conservation of the total linear momentum along the direction of impact. So here, if we assume that these two rigid bodies are hitting each other at point P, and the common tangent is y, common normal, or the direction of impact is x, so it's like the total momentum along x direction for the system is going to be conserved or not changed. So conservation of total linear momentum along the direction of impact, which, as I said, in this case it is equivalent to the x-axis. Then if we want, we can say no change in the momentum of individual or no change in the individual momenta along the tangent direction, correct? So if we assume in the tangent direction no force is exchanged, like in this case, we assume that friction is negligible, then we can say along the y direction, the momentum of each one of these components, not the total thing, the momentum of A is not going to change, the momentum of B is not going to change because no force is exchanged, so momentum of individual parts is not going to change. And then conservation of the total angular momentum, if we can find a point along which if we can find a point about which the total moment is zero, then we can say that the total angular momentum about that point is not going to change, right? So we call it conservation of the total angular momentum, and in specific cases it could even be individual angular momentum about some points. Now, which points are typically candidates? One of the most important points is typically the point of impact, P, because the forces are exchanged over there. So if we take some of the moment about that point, if we neglect other forces like gravity, which we do here during the impact, then we can say that the total, and you can say even the individual momentums, angular momentums of the part about that point is fixed, because of course that's the only point that there is any force, and when you take moment about it, of course the total moment is going to be zero. So about, let's say here, let me say about the contact point. Okay, that's definitely one of the ideal points to take a moment about. Okay, and finally we have the coefficient of restitution. Now, the definition of coefficient of restitution is important. So in the past we had two particles. These two particles hit each other. Their velocities before impact, we call them VA, VB, and after impact we call them what? V prime A, V prime B. And so the negative of relative velocity after impact to the relative velocity before impact was what we called coefficient of restitution. And if the impact was 2D, like an oblique impact, please watch that video I made, then again the definition was the same. The only thing was all of those velocities, we only focused on their component along the direction of impact, in this case let's say x. So we still wrote that equation, negative relative velocity after to relative velocity before impact, but all of those relative velocities were along the direction of impact, as I said, let's say in this case x. So that was the definition. Now in here, when we say velocity of points, well, this is a rigid body, and we know in a rigid body different points have different velocities, right? So which velocity should we include in this coefficient of restitution, right? Because it's not like a particle that only has one velocity. It has infinitely many different velocities. Which point do we include? And the answer is, of course, the point of contact, right? Because that's where the impact is happening. So what we need is this. We say negative of the relative velocity of the what? Of the impact points calculated from each body to the same thing before impact. So after impact and before impact, and everything is only x component. So when I say v prime of b at point P, how do I calculate it? Well, I calculate the velocity of the centroid after impact and then add it to this term here. Now here I have to use the cross to make it correct, because here there is actually a cross, and if you don't show that, it is not going to be shown well. So here there is a cross term, of course, and if you see here I use bold font, so bold font means they are vectors. Okay, so I use the general relative velocity formula for a rigid body, which v of any point is v of another point plus omega of the rigid body cross r that connects those 2 points together, the relative position. So here I'm using this formula 4 times, 1 time for each object and 1 time for before and after impact. So each one of those terms in this coefficient of restitution formula, they come from these formulas, and they can have in general x and y components. All we care about is their x component. Only the x component all goes into this formula. Okay, so you clearly see that how I'm trying to use my formulas and what I learned, correct? Principle of linear impulse and momentum, principle of angular impulse and momentum, coefficient of restitution and everything to solve the problem, right? So now with all that said, let's focus on this problem, which is an interesting one, and see what happens in this case that these two similar cars are going right at one point and hitting each other, and then after that, you know, their velocities of centroid would change and they would start doing the yaw motion. They would turn, so they will get some omegas. We don't know any of that. We have to find it. And again, here to make the life a little bit easier, we assume there is no friction at point P, so all the force exchange is along y direction, nothing along x direction. Okay, so the fact that there is no friction at point A, it means this guy here, this rule number 2, that individual momenta along the tangent direction, which is x here, they are not going to change. So what I want to do is, since what I care about is the velocities of the centroids, let's write down the velocities of the centroid before impact. So how much is v of the centroid A before impact? When there is no prime, it means it's before impact. How much is it? Well, if I use this x and y, clearly you see the magnitude is 30, the angle is 20, it is going in the negative y and positive x direction. So it is going to be 30 times cosine of 20 degrees I, and then minus 30 times sine of 20 degrees J, meters per second. Okay, so that is velocity of the centroid A, and you can do a similar thing for velocity of the centroid B. That is just 20 and I, so that's easy. It's simply 20 I. Correct? And now these guys, these vectors, you know, they have x component and y components. Their x components should be the same as the x components of the same thing before impact, because there is no x force. Okay, so it means sum of the x force is equal to 0 for each one of the objects. That means that v prime of let me write it separately. It means that v prime of centroid A, the x component of it, is the same as v of CA, the x component, which is this guy here. And it is 30 times cosine of 20 degrees. That is not going to change because no x force is applied to it. The same thing for object B. V prime of C of B, the x component, is the same as V of center B x component, and that is equal to this guy, 20. Okay, so how many unknowns in general do I have to solve for? You know, each one of these vectors, it has x component and a y component. So there are 4 unknowns here. and I have two omegas, and omega is about z, so there is only one magnitude unknown, so that's also 2 unknown. So overall, I have 6 unknowns. Okay, I have 6 unknowns, and here 2 of them are fixed. I found the x component of the velocities after impact for the centroid. So 2 of them are good. I need to know 4 other ones. And so far, the only thing I have used is this guy, that the individual components along the tangent direction, which in this case is x, they are not going to change. So I have used rule number 2. Now let's use the other rules, 1, 3, 4, and so on, and see what they can give us. Okay, so if we go about rule number 1, it says the total linear momentum along the direction of impact, which in this case it is y direction, that is not going to change. So what does that mean? It means ma times v of ca, the y component, plus mb v of cb, the y component. This is the total momentum of the system before impact along the y direction, is the same as ma v prime of ca y plus mb v prime of c of b y. Okay, that's rule number 1. And here the m's are the same. Both cars have the same mass, so I can get rid of this. And I can plug in the values for y. So the y component of velocity of CA before impact is this much. For B, it is simply 0 times J, correct? So this guy is 0. And this guy is negative 30 times sine 20. And these 2 are unknown, as you know. So that is one equation so far. Let me number that and call it equation number 1. Okay, so so far I have 4 unknowns left, and I have 1 equation. Good. I need 3 more equations. Where do I get those? Well, I have to go about this rule number 3 now, which says the angular momentum of either total or individual components about the contact point is constant. Why is that? You know, in general, for any object, you can write that sum of the momentums about the centroid or a fixed point, right? You can write it as sum of the moments about, let's say, the centroid is equal to time derivative of total momentum of that single part about the centroid, right? The angular momentum. So this is the rule that we can write, right? And you know it from previous videos. Or you could also use, instead of point C, you can use point O, which is if there is a permanent fixed point on the rigid body, you can also use that. Now the question is, what about point P? Can I write some of the moments for each part, not both of them, just for each part? Can I write some of the moments about the point P for each part and say this is equal to rate of change of angular momentum of that part about point P? Does P qualify for the simple version of the angular momentum equation? Okay. And if it can, then how much is this sum of the moment about point P? Well, if I can, that's good, because you know the only force here exchange between these 2 objects, or let's say if I show it here on the cars, the only force that is exchanged is along the y direction, right? So this is like F of B on A, and this is F of A on B. And so if you take sum of the moments in each part about this point P, of course, the only force existing passing through point P. So the left-hand side, this guy here is going to be 0. The only question is, can I write it this way? Okay, or because point P is not the centroid, is not permanently fixed point, do I need to add my extra term that we talked about in the previous videos? So if you remember in one of the videos that was called Planar Equations of Motion, I proved to you that if point P is arbitrary point, and it's not centroid, it's not a fixed point, then if I want to write the angular momentum equation for it, I have to write that sum of the moment about that point is I about the centroid times alpha minus r of that point with respect to the centroid cross MA CM. And you can write this in another way too. So let me write that in another form for you. So here you have your rigid body. This is point P. This is the centroid C. And you know the centroid has angular velocity omega, and it also has the velocity of the centroid. And the whole mass is conserved here. You can say concentrated here. So if I ask you what is the angular momentum of the system about point P, not about point C, because if I say what is the angular momentum of the system about point C, based on one of the formulas I proved on that video, you know that it is equal to a moment of inertia about point C times omega, correct? That was what we had. Now if I say what is it about point P, so basically what I'm doing here is called transfer of angular momentum. Can I transfer angular momentum from C to P? Yes. It says the angular momentum of P is the same as what it was about C, plus if you concentrate all the mass at the centroid and put the velocity of the centroid there, and this vector here, which is r of C with respect to P, if I say I have a particle with mass m, velocity c, which is located using this vector r of Cp from point P, what is the angular momentum of that single particle from point P? You know the definition of angular momentum was r cross mv, correct? That's what we had. That's the original definition. So you say yes, that is equal to r of C with respect to P cross m of the part times velocity of that point, which is v of C, correct? So again, what I have done here is called transfer of angular momentum. Good. So now if I say, could you take a derivative from this for me? D of hp with respect to dt. Could you take a time derivative? And you say yes. It is going to be the derivative of hc, which is this guy. And here, if we assume ic is constant, it is going to be ic times alpha. And then instead of r of Cp, what I want to use is the opposite of that vector, which is r of P with respect to C. So instead of this, I say it's negative of r of P with respect to C, if you don't mind. So it is going to be minus r of P with respect to C. And then what? Cross MVC, and you know MVC, if M is constant, it is going to be M times A of C. Correct? Now here you might say, well, what happens to the derivative of this term, because it's a cross product of two vectors. So fine, you can write that as negative of the other one. Here you took a derivative of the second term times first term, that's fine, but you neglected one of them, which should be basically negative of the time derivative of this r of P with respect to C with respect to time cross MVC. right? It's a product term, so when you take time derivative, it has two terms and not one. If you look at this point until here, this guy is exactly what we had in that formula. I about Cm alpha minus R of P with respect to Cm cross MACM. Okay, this is exactly that. So if this term is 0, then, right, this guy here, based on that formula, should be equal to what? Sum of the moments about P. So this one should be equal to sum of the moments about P. The only question is, what is this guy? If I can do something with that term, then I can get to a simple form, which is sum of the moment about P is simply dH about P over dt. Okay, as long as, again, I said this term is eliminated or neglected or something, then I can write it this way, and then I can say that on each part about point P, since the only force is applied on point P, this moment about point P is 0. It means that H about point P is gonna be constant from before to what? After impact. So I can say sum of the angular momentum, or not sum, the angular momentum of each one of the parts in impact about the contact point is going to be what? Constant, which is what we talked about here. Remember, we said that the conservation of individual angular momentum about the contact point, which is h of p, is constant. Well, that can be done when m about p is 0. In this case, it is. During the impact, the only force is applied to point P, so sum of the moment about P is absolutely 0. The only obstacle is this guy here. Is this term 0? Well, here, this R of P with respect to C has a constant magnitude, but it does not have a constant orientation because it does rotate. It does rotate, and you know, since it is rotating with angular velocity omega, the derivative of it is omega cross R of P with respect to C. Correct? That's the derivative of a vector with fixed magnitude but rotating with angular velocity omega. Now, what about this? What about this term? Omega cross R of P with respect to C. What is that? When it's cross multiplied now by MVC, what would you get? Okay, do you think this term is going to be 0? That's the thing. Okay, yeah. Now, how can I write V of C in terms of V of P? You know that V of C can be written as V of P plus omega cross R of C with respect to P. Correct? That's the definition of velocity of the centroid. And now, if this V of P is somehow 0, then what I'm doing here is this R of C with respect to P is negative of R of P with respect to C. What I'm doing is I'm cross-producting a vector and the negative of that vector. And you know, cross product of the vector and the negative of it is always what? 0, right? Any vector cross itself, the result is 0. So I can get there as long as I can show that this contact point is momentarily stationary. If the contact point is momentarily stationary, it does not move, then I can say that yes. Okay, so this is using some assumption. During the impact, can I say that the contact point is momentarily, it doesn't need to be all the time, and you know it's not a permanent fixed point, can I say momentarily the contact point comes to a rest? Okay, when two objects hit each other, can I say momentarily that the contact point is stationary? Well, that's what is not discussed here in this textbook. If you look at the textbook by Bedford and Fowler, it has not discussed any detail like this. It just jumped into the conclusion that yes, the angular momentum of each part about the contact point is constant. And it never mentioned any detail like that, okay? So it just simply neglected it. And I do not really like that idea that you can simply just neglect everything and not talk about it. So it comes down to this, okay? Now, in some applications, you can easily say that, like, for example, if you have the wall and you're throwing something at the wall, or let's say there was another example that we had in the textbook where you had a pendulum, stationary pendulum, and a ball is hitting it, and then it is asking you to find the omega of the pendulum and v of the centroid after impact. So during the time of impact, which is a fraction of a second, since this guy was stationary, when the ball hit it, there is the touch with the point P, and the point P is on the stationary object right at the time of impact. So yes, here I can absolutely say that V of point P was 0, and I can use that conservation thing here. But the thing is, when these two cars hit each other, okay, during the impact, this point P belongs to each one of these cars, right? There are actually two P's, one P for the top, one for the bottom one. At the moment, they are on the top of each other, but they are on the two objects that are moving. They are on the two objects that are moving. So assuming that the contact point here is stationary is a little bit out of ordinary to me, if you ask. So going back to what we had, as you can see here, if I simplify everything in this equation here, then since for the case of impact, every force is applied to point P, definitely this guy is 0. So if I simplify it, it will be dH with respect to P over dt is equal to, and as I said here, this portion of the cross product, this portion times that omega plus R of C with respect to P is 0. So what you will have is going to be omega cross R of P with respect to C cross V of point P. Okay, so this is the true form. If you take some of the moments, as I said, of course, this is plus some of the moments about P in general. And this, for us, in the case of impact, this is 0 for each object. This is definitely 0. But here, if you want the whole thing to be 0, so that we can say h with about point P is constant, then this term should also be 0. And as I said, either V of P has to be 0, which in the case of these two cars is not 0. The only justification you really can have for this case to take the whole thing to be 0, as I said again, this is 0, is since V of P is not 0, the only thing you can do is this omega. And in this case, before impact, both objects have no omega. So none of the objects is rotating before impact. So, and since the impact is just a fraction of a second, if you write this equation right at the time of impact, you can assume that this omega is what? 0 momentarily. Okay? Because after impact, of course, omegas would change from 0 to non-zero values, and we are going to find them. But again, just because of this case, omegas of the two objects right before impact was 0, and omega has to continuously change. Of course, at the time of impact, it changes all of a sudden. There is no continuity. But just for that fraction of a second, since before it was 0, I can say right at that point, I assume like it left continuity, and I say, yeah, the omega at that point was 0, so I basically exploit this condition and then say, yeah, this whole thing is 0 now. So when this whole thing is 0, then I can say, yes, h about point P for each one of the objects is 0. Okay, so it needs one of these two conditions. Please keep that in mind, because in the textbook it says you can always assume this. Unfortunately, your book here, or not your book, maybe Bedford and Fowler, assume that this is always true. That's not the case. It is absolutely not the case. Okay, unless one of these two conditions is true. Either one of the objects is stationary before the impact, or the objects were not spinning or having no rotation before the impact. In this case, one of the conditions is true, so we can say that. So yes, in this case, I'm going to exploit that condition and say, because of that, and because there is no friction about point P, or even if there is, when you take moment about P, all of those moments will go away. Then I will use this condition. So now I say that the momentum, the angular momentum of object A about point P is going to be constant, which means whatever it was before impact is going to be whatever it is after impact. Okay, and now what do I gain from that? Well, what is the total angular momentum of object A before impact about point P? Well, you know, angular momentum about point P can be written as angular momentum about point C, and then plus what? Plus, as I said, if you assume the whole mass is here and the velocity is v of c, so the linear momentum is mvc, and this term here, this r of c with respect to p, if you cross it times mc, that is a momentum of c with respect to P, and if you add the angular momentum due to IC times omega to it, then some of those will be angular momentum about P. So if I want to write this, this is going to be what? This is going to be I of CA times omega A, and then you have to look at the direction of this vector, R of centroid A with respect to P cross MV of centroid A. This is the same as I of CA omega prime of A plus the same thing, R of the centroid A with respect to P cross MV prime of CA. Okay, and now the thing is, you know, before impact, omega of object A was 0, and then V of CA is completely known, so I have this guy completely, this M I have it, omega prime I don't know, V prime CA, it has an X component and a Y component, X of it I know, Y of it I don't. Okay, and from here, and you know IC, you know it, you know M. So if you know this R of CA with respect to P, which of course we can find through the diagram, then this should give you an equation. this should give you an equation. So what we need is first this vector r of CA with respect to P, which, as I said, that's this vector here. Okay, so let me clean up and get that vector together. So that is this vector. This is r of CA with respect to P. Okay, how can I write it? Well, it comes from these dimensions, right? So it is this vector. As you can see, it is 1.8 meters along the direction of the car and 1 meter perpendicular to the longitudinal direction of the car, transverse direction, and they have to both be decomposed with this angle 20 degrees, right? Because this 1.8 is along this direction, which makes angle 20 degrees with x, and so it has to be decomposed along x and y, and then this 1 meter also, correct, which is like that, that has an angle of 70 degrees, correct? So this angle should be 70 degrees, and this angle is 20 degrees. So that 70 degrees should also be decomposed along x and y. So if we want to write it, it is going to be 1.8 negative x positive y. So let me write it. R of CA with respect to P is equal to negative 1.8 cosine of 20 degrees I plus 1.8 sine of 20 degrees J. This is for that 1.8, and then plus, we have now this vector of 1 meter angle positive 70, and it's both positive x positive y. So it is going to be 1 meter times cosine of 70 degrees I plus 1 meter sine of 70 degrees J. Okay, so this is R of CA with respect to P. And as I said, if you put it in this top equation, and also knowing that V of CA was, if you remember, we had it up here, it was that 30 cosine to any I minus 30 sine to any J. So this omega prime A, you can write it just as magnitude of it in the K direction. And this V of C prime of A, remember it has an X component, which we have, and it has a Y component, which we don't, right? So if you write it, because you have a bunch of cross products, you better do it using matrices in the 3x3 determinant. So what you have here is you have the R cross MV vector. So it is going to be I, J, and K. Your first vector is basically this guy. The second vector is M, V, C, A, and remember A is 900 or 1600, so you have to multiply it by this number. If I do that, what do I get? So here I calculated this relative position vector. It is negative 1.35 I, and then plus positive 32J, and there is no K, so that is my first vector. And then what you need is to multiply M, which is 1600, by this V of CA, correct, before impact, and then plug it down into the bottom row of the determinant, which I'll do right now. So here I just calculated it. It is going to be 45,105 I minus 16,417 J plus 0K. So I replaced it down here. So that is this term on the left. Then we have ICA, which is given as 19,600 times omega prime A times K. So that is this guy here. And then for the second one, again, I need to form a determinant. So I have I, J, and K. Again, R of CA with respect to P is this very same vector. And now I have to multiply 1600 by the components of V prime of A, for which the X component is the same as what it was. The Y component is unknown. So what you will get is the X component is going to be this 45,105. It's unknown. It's known. The other one, which has the Y component, and I don't know it, I am going to write it like this. I'm going to write it as 1600, which is the mass, times velocity of the centroid A, the Y component of it. This is one of the 4 unknowns remaining, and then 0K. Okay, and once you calculate this, if you look here, once you calculate the determinant, all you will get is K here, and all you would get is K here. So everything is going to be K, and so that will give you one scalar equation, which I'm going to write right now for you. So here I expanded it. By the way, this guy was 960, 990, So this is the equation you will get for 2 of these unknowns. Okay, V omega prime A and V prime of C of A in the Y direction. So that guy I call equation number 2. If you remember, this guy was equation number 1, which if I write it properly, it is going to be negative 30 sine 2n. So this is going to be V prime of CAY plus V prime of CB y is equal to negative 30 times sine of 20, which it is negative 1026. And this guy, let me call this one equation number 1. It's better to call this one 1. Okay, because that's written nicely. Okay, so I got equation 1, I got equation 2. I need to write a very similar equation, this time for a constant angular momentum, but instead of writing it about object A, I will write it for object B about point P constant. So it is going to be quite similar in nature, right? So I have to say H of about point P of object B before impact is the same as whatever it is after impact. Okay, so I can write it about object B, and again I have to transfer momentum from the center to the contact point. So this is going to be I about CB times omega B plus R of, as you can see, it's just exactly similar to that, except CA becomes CB, correct? So this becomes CB with respect to P cross M at V at the centroid. So this is what it is before impact, and then you have a similar thing for after impact. Okay, and again I have to replace everything. So you know this guy was initially 0, and this omega B prime I don't know. I can write it as its magnitude in the K direction, where the magnitude is unknown. I know I know M, R of C with respect to B I can find from the picture. This VCB prime, it has X and Y component. The X component is 20, just like it was, as you can see. The Y component, I don't know. So this is like 20I, and then plus whatever the Y component of it is in the J direction. Okay, so the two unknowns are omega prime B and V prime CB of Y. Everything else should be completely known. This V of C B also was 20I. So everything is rather clear here. As I said, the only thing we need to do is R of C of B with respect to P, which again we have to go back to our diagrams. And since P is here, that is center, this is this vector. R of C of B with respect to P, which is very easy because this object is not tilted, so it's simply negative 1.8I and negative 1J. Okay, so that is much simpler. And so if I plug in everything into that top equation, you will get again a determinant I, J, and K. And here you have the R vector, which is negative 1.8 and negative 1 and 0. And then you have M times VB, and M is 1600 multiplied by 20. So you get 32,000 I. No J and no K. This is equal to 9600 times omega prime B in the K direction, and then plus another determinant where again you have the same R vector, and here this 1600 is multiplied by that, so the 32,000 is the same. Here you have 1600 times V prime of CB along the Y direction and 0. Okay, again, if you expand it, it should give you another scalar equation. Let me use a little bit thicker pen. And if you do that here, you see that the only term you have is positive 32,000 on this side. On this one you have 9600 omega prime B. If you expand this one, you will get plus 1.8 times 1600 that, and then plus some 32,000 again. Okay, so or negative. This guy is going to be negative, and this is going to be V prime of CBY, and the coefficient of that is going to be 1.8 times 1600, which is 2880. And of course, you can get rid of this guy here. So this one is easier because now you have basically a linear relation between them, right? One of them is a multiple of the other, and this one is going to be your equation number 3. Okay, so now you got your equation number 3. You got your equation number 2 up here, and you got your equation number 1. So 3 out of the 4 equations we need are now here. The only thing remaining is, so now I have used this one. The only thing remaining is this guy, coefficient of restitution, which is E here is 0.2, is negative of what I have from here. Okay, so I have to calculate the velocities of point P on each object from before and after impact, and look at their x component and find this ratio of relative x components, set it equal to E. So for that, as I said, I need to go and find the velocity of point P on object A before impact. It is equal to velocity of center A before impact plus omega of the object before impact cross r of that P with respect to the center. Now, since there is no rotation before the impact, this whole term is going to be 0, which makes life a lot easier. So it is simply going to be the same as VCA, which was negative, as you can see here, it was 30 cosine 20 minus 30 sine 20. Okay, so it was 30 times cosine 20i and minus 30 sine 20j, and the only component I care about is this guy, the x component. That is what goes into that E equation. And the same thing goes for point P on B before impact. Again, object B does not have any rotation, so this whole term is 0, which makes life easy, and that just makes it equal to 20i and plus 0j. Again, I don't care about the j, all I care about is this guy. So we underline them so later we can incorporate them into the E equation. And then the very same thing has to be repeated for after impact, where now I have unknown angular velocities, an unknown velocity of the centroid, at least the y component of it. So it is going to be like this. Okay, so for V of C prime A, the x component of it is going to be the same as whatever it was, correct? Which is that 30 cosine 20. It's not going to change. And the y component of it is unknown times j. So this is the velocity of the centroid after impact. Omega prime, I don't know, I just assume it is in the k direction. And then cross r of P with respect to CA, which I guess I have it somewhere up here, right? R of, this is C with respect to P. If I want P with respect to C, that's the same as this vector, just negated, right? So positive 1.35, negative 0.32. Good. So once you have that, then now you can carry out the cross product here and add them together. And if you do, here you have k cross I, which is j, and then you have k cross j, which is negative I, but there is another negative, so you get positive I. So your I component is going to be 30 cosine 20, and then plus 0.32 times omega prime A. This guy is times I, and then your J component is going to be VCA prime Y, and then plus 1.35 omega prime A. And again, all I care about is this I component. Okay, and then I have to apply something similar for point P on B. So this prime CB, correct? It has an X component and a Y component. The X of it is 20. The Y component I don't know, so I just write it as is. Omega prime B, I just write it as omega prime BK cross, now R of P with respect to CB, which is the same as CB with respect to P, just negative of that. So both of these guys are going to be positive. So this is going to be 1.8 I and plus 1 times J. And again, here you have to carry out the cross product and add the i's and the j's together, which if you do, you are going to get 20. You have k cross j, which is negative I, so you will get negative omega prime b times I, and then your j component is v prime of cb y, and then k cross I is j, so plus 1.8 omega prime bj. And again, all I care about is the I component. So now these I components that I underlined here, 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 and here, we plug them all into the E equation. And we say E, which is 0.2, is negative of the subtraction of the I components of P on B and P on A, which is this guy, minus this one, and then the same thing for before impact, which is 20 and 30 cosine 20. Okay, and if you cross multiply from here, you will get another equation, which if you want I can write it for you, right? So it is going to be like omega prime b, and then plus 0.32 omega prime a is equal to, and here I have done the arithmetic and found the number, and the number was negative 9.83. So this is finally my equation number 4. So now if you look at 1, 2, 3, and 4, there are 4 unknowns in them, the 2 omega primes and the 2 Vy components of the centroid. So I have 4 equations and 4 unknowns, and so finally if I solve them from 1 and 2 and 3 and 4, I can find my unknowns. And And remember that the x components of the centroid were already found. They were constant, they were not changing. So it was the y component of the velocities of the centroid and the omegas that were changing. If you do that, this guy is going to be 2.65 radians per second. The other one is going to be negative 3.54 radians per second. This is going to be negative 9.08. And this guy is going to be negative 118. Okay, and remember the x components, if I just write them from what we had in the past, the x component for this guy was 28.2, and the x component for the centroid of B was 20. So these are determining the speed of the centroids after impact, and these are the omegas. Now, do they make sense? So this omega means counterclockwise, this omega means clockwise. This velocity here has positive x and negative y, so it is something like this. And this one is positive x and negative y, so that also means something like this. Does that make sense? Absolutely. If you go back and look at that, so they are coming like this at each other. One of them at angle, the other one is horizontally, and it says when the impact is happening due to impact, this guy is changing the values of it, right? Initially, it was going with 28 and let me see how much it was. So it was 30 times sine 20, right? Negative 10.26. Okay, so the y of it was negative 10.26. Now it is changed to negative 9. So it means if it was going like this, now the angle of it is a little bit, should be upward because the y component is reduced. So instead of this guy going straight, if this is where it was going, now it is going a little bit further up like that because the y component is a smaller negative number. And this one that was going straight, what happens to this? Now this one has the same x of 20 but y of negative 1.18, so the y of this is also like that. And you know this is absolutely reasonable, right? Because the forces that were exchanged were like this. This force was applied to the top car, so of course it is going to change the Vy of it a little bit upward, and it did. And this force was applied to the bottom one, so it has no y, so now it has a little bit of small y downward. So the directions completely make sense. And then it says this one is rotated counterclockwise. Of course, if you were going like that, and now you're going like this, you have to have a counterclockwise rotation, and for this guy we're going straight, and now you're going a little bit further down, you have to rotate what? Clockwise. So you see everything is completely making sense. So I know the video was long, but I just wanted to tell you that solving an impact problem in rigid bodies is not as trivial. You have to exactly know what you're doing, exactly apply all of the equations, know where there are simplifications you can make and so on. And instead of let's say, it was two unknowns that, or actually it was two unknowns in particles, only the y component because the x's are never changing. So instead of 2 unknowns that you had, now here you have 4 unknowns. The omegas will be added as well, so the problem is more involved. And getting those equations also needs a lot more calculations because here you are involved with cross products. But hopefully I could make the topic clear, and thank you so much for your attention. See you in the next lecture.